Hello everyone, I am Bindusree, working as an assistant professor in the Department of Electronics and Communication Engineering at Institute of Aeronautical Engineering and Technology. So my subject is the high-speed communications. In that, today I am going to discuss the topic is minimum shift keying. So in the minimum shift keying, before that one more technique is the phase shift keying. So this is also one of the digital modulation technique. So in this phase shift keying, it is depending on the phase of that particular signal. So it does not depending on the amplitude as well as the frequency of the signals. So that is the phase shift keying. So next one is in that one. So we are going to discuss the topic is the minimum phase shift keying. So MSK is the minimum shift keying. It is a type of continuous phase frequency shift keying. So that means, so here no discontinuities in that particular signal. So it will be continuously taking the phase angle of that particular one. So that is the continuous phase frequency shift keying. So it uses the minimum frequency separations to achieve orthogonal signals. In the orthogonal signals, at a time we can take the multiple signals, but we cannot interfere the one signal to the another one. So that is the orthogonal signals. So it is the final of this using the orthogonal signals. So here the spectral efficiency in the modulation scheme only. So the minimum shift keying is also one of the digital modulation technique. So here it is the phase of that particular signal will be the continuous. It creates a constant envelope and smooth transition between the digital data bits. So constant envelope means it maintaining the constant amplitude and the smooth transition between the digital data bits. So if you are taking any analog signal, so this is the digital modulation technique. Automatically here we are taking the digital data bits, so that the digital data bits will be maintaining the smooth transition and it creating the constant envelope. So why? Because it is not depending on the amplitude. So it will be so no need to worry about the amplitude of that particular bits. So that's what here the constant envelope is there. So generally, we are taking the bits is the binary data bits. If you are speaking about the any type of the phase shift keying or the frequency shift keying or the amplitude shift keying, so either we can talk the QAM, whatever it is. Before that one, we are talking about the binary shift keying, either the frequency, phase, and the amplitude, whatever it is. So why? Because so the digital modulation technique is indirectly depending on the digital bits. So the digital bits are the zeros and ones only. So here we are taking the 0 state as well as the 1 state is there. So that is the bits are 1 and so by using these zeros and ones, now we can create the signals. In that signals, we can take that particular carrier frequency. If you are taking the any modulation technique, so the message signal as well as the carrier signal is the must. So here we are taking the extending the long way from the carrier. So why? Because so by using this one, if you are getting the any high any sidebands will be occurred, so that will be extends to that particular carrier frequency. So this will be creating the problem for the radio communication systems. So why? Because it occupies the total spectral bandwidth, so it might be having some noises will be occurred. So that is the main problem in the radio communication system. So any sidebands outside of this bandwidth, so it can interfere the adjacent channels. So and any radio communication that may be using them. So for example, this is our total bandwidth. So this is our total bandwidth. So for example, here the sidebands are there. Side lobes are there. So this is our total spectrum of this bandwidth. So for example, any side lobes will be occurred outside of this bandwidth also. That may be one of the interference of that particular adjacent channels. So that is the one of the drawback of this one. So next one is the minimum phase shift keying is having the no phase discontinuous. So that means it will be maintaining the continuous frequency shift, continuous phase shift keying. So that means continuously it will be moving to that particular bandwidth. So for example, no discontinuities will be occurs. So that means whatever the signal will be occurred, whatever the signal we want, so we can take that particular signals only. So that's what no discontinuities is there. So automatically the bandwidth will occupy the overall message signal only. So it will not be occupied the unnecessary data. So automatically the bandwidth efficiency is the high. So it reduces the bandwidth of that particular signal. So next one is to overcome the filtering the signals. So by using this one, so we can overcome the filtering the signals. So the data becomes a progressively less sharp the level of the filtering and increases the bandwidth. Filtering is increases, automatically bandwidth will be the reduces. So the advantage of the MSK is the continuous phase shift scheme. So by using the modulating data signal changes frequency of the signal, so there are the no phase discontinuities will be occurred. So from the starting onwards, we are concentrating only on the MSK is the continuous signal. So it is not depending on the no phase discontinuities. So that is the main uniqueness of this MSK. So the differences between the logic 1 and the logic 0 state is also the half of the bandwidth. So that means if you are taking the bandwidth is the 0.5 FP. So that means the bandwidth between the logic 1 to the logic 0 is the half of the bandwidth. So that is the R 1 by 2 of the FB. So that is the 0.5 FB. So this is expressed by using this one we can find the modulation index also. The modulation index is always equal to the 0.5 FP. So this is the particular waveform, that is the minimum phase shift keying. So for example, here we are, this is the data, this is the binary data. That's what here we are taking the square waveform. In the x-axis we are taking the time, in the y-axis are the bits. So 1, 0 and 1, 1. So that means coming to the MSK signal, if the 1 is there, so that is the low frequency of the signal. If the 0 is there, that is the high frequency of the signal. So here we are between this duration. So here we are taking the high frequency of the signals. Between these durations, here it will be taking the low frequency of the signal. So based on this one, so we can draw the waveforms for the MSK by using that particular data bits. So next one is this MSK. This is the minimum shift keying. In this minimum shift keying is depending on the. So initially we are taking the 1 bit. Initially we are taking the multiple bits. So for example, that bits are the 1 0, 1 1, 0 1, 0. So this is the binary bit. This is the binary bit. By using this binary bit, so now this bit will be converted in terms of the signal format. So that is the 1 0 1 0 1 0. So this is the binary bit signal. So this is the input bit. So next one is the next step is the unipolar NRZ value. So that will be maintaining the zeros and +1 and -1 volts. So that means if you are taking the binary bit is the 1, so this is the starting bit 1. If the binary bit is the 1, so that is the in the unipolar non-written 0 value also 1. If the binary bit is the 0, so that is the +1 volt. The +1 is the +1 volt. So coming to the 0 is the minus 1. Again for the 1 we can take the +1. Again for the 0, -1. 1 is the +1, 0 is the -1. So this is the unipolar non-written 0 value. So next we can take the odd bits as well as the even bits. So this is the binary input bit. In this binary input bit is having the odd number of the bits are there and the even number of the bits are there. So for example, this bit index value is 1, 2, 3, 4, 5, 6 and 7. So now we are taking the odd number of the bits, so that is the B naught of t. So that means, so initially we are taking the 1, next one is the 3, next one is the 5 and next one is the 6. So now we are considering the 1, 3, 5, 7 bits only. So each and every bit. So here we are not taking the even number of the bits. So that's what the odd number of the bits will be combining with the even number of the bits. So that means instead of the single bit, we can represent the two symbol of the bits. So for this one, so initially 1 is there, now we are considering the 1, so that is the odd bit. So for this odd bit, now we are taking the up to this one. So next one, again we are taking the 1, so that is the same bits, so that will be taking the two symbols. So next one is the 5th bit, so this is one more of the odd bits, so that is the 0 and this one. Next one we are considering the 0. So up to this. So here the 2 bits are there. Okay, this is the odd bits. So similarly we can take the even number of the bits. Similarly we can take the even number of the bits. So that means now considering the 2, 4 and 6 is there. 2, 4, 6 is there. So that's what in the even number of the bits we are not considering this first bit. So that's what the starting bit is. The starting bit is this one. So that means here we are taking the starting bit is the 0. So here also same procedure, whatever the procedure we are following, the odd number of the bits, same procedure also here following. We are following the same procedure for this even bit also. That means for the single bit, so we can transferring the combination of the 2 bits. So initially 0, 0 is there. So up to this one. This is the 0 bit. Next we are considering the 1. So again we are taking the 2 bits. Next one 6 is there again. For the 2, now we are taking the 2 and 3. For the 4, so we can take the 4 and 5. So next one we are taking the 6. So that will be taken 6 to 7. So this is the odd number of the bits and this one is the even number of the bits. For the odd number of the bits and the even number of the bits, we are taking the cos omega ct for the one carrier frequency. And for the even signals, we are taking the another carrier frequency. So that is the sin omega ct. So for this cos omega ct will be starting from the, this is the cos omega ct value. Okay, this is for the sin omega ct value. Okay, so this is for the cos omega ct, this is for the sin omega ct value. So here we are taking the two different carrier frequencies. Two different carrier frequencies. Okay, so this one is for the cos omega ct and the one is for the sin omega ct. So now multiply with the b naught of t into cos omega ct. B naught of t into cos omega ct. So here we are concentrating on the non-return 0 values. So that means that cos omega ct is multiplied with the 1 is the cos omega ct. Now if you are multiply with the minus 1, so here the minus 1 volts is there, this is the 0 and this one is the plus 1 volts. So the odd number of the bits are multiplied with the cos omega ct. So that is the cos omega ct one only. So if you are multiplying with the minus 1, so that is the minus cos omega ct. Okay, so here the phase angle is the cos omega ct plus. So here the phase angle will be the changes. So so for example, this now we are concentrating on the b naught of t into cos omega ct. So that means here up to this one, so in the b naught of t into the b naught of t into cos omega ct, multiply with the b naught of t into cos omega ct. So here we are concentrating on the phase angle. Whenever the phase, the bits will be changing from the 1 to 0, automatically the phase angle will be the changing. Okay. So based on this one, so first one we are talking about the b naught of t into cos omega ct. So b naught of t is starting from this place only. Okay, so now up to this position, whatever the signal is there, same signal will be presenting here. So that means 1 into cos omega ct up to this one. So now the bit will be changing from the 1 to 0. So automatically the phase angle will be the changing. So here the waveform will be stopped here. Now the next one will be starting from this place. So this is the cos omega ct and the cos omega ct plus pi. So are the pi by 4. So this is the b naught of t into cos omega ct. So next one, b of t into sin omega ct. B of t into sin omega ct. So now multiply with so the starting bit is starting from this place only. So this will be multiply with the sin omega ct. So here the phase angle will be the starting from this bit is starting from this place only. So initially whatever the sin omega ct is there, so that will be starting from the 0. So for example, this is the b of t into cos omega ct. So up to this one, same bit will be there. So now this will be changing from the 0 to 1. So in the b naught of t into cos omega naught t, so that is the out of phase angle. So here the b of t into sin omega ct, so this is the in phase of the angle. So now concentrating on this one, so these bits are the 1, here the 1 is there, here the 1, next one is the 0, 0 as well as the 0. So coming to the b of the bit, so this is the starting bit, so 0, 0, 1, 1, 1, 1 is there. So now combining of these two bits. So initially the b of t no signal is there. So that's what here we are not concentrating upon this bit 1. So next one, this is the 1, 0. Next multiply with this one 1, 0. Next one is the 1, 1. So next one is the 0, 1, 0, 1, 0. So that means, so here the same number of the bits is there in that one high frequency of the signal. So odd number of the bits are there. So that is the low frequency of the signal. So that means, so for 1010, again 1010. So coming to this 11. So here the high frequency of the signal. So this is the phase angle of this one. So no discontinuities of the signals. It will be continuously monitoring of this phase angle. So this is the MSK of the phase angle. So here the multiply with the odd number of the bits to the cos omega ct and the even number of the bits with the sin omega ct. So next one is the MSK modulation. So in this MSK modulation, initially we are taking the binary bits. Next one we are giving this product modulators. So that is the cos omega ct omega c plus omega bt by 4 high frequency of the signals as well as the low frequency of the signals, omega c plus omega bt by 4 and omega c minus omega bt by 4. So next one we are taking the cos of the signals, and the next one we are taking the product of these modulators and summation of these two signals. So that is initially here we are taking the binary bits of the signals. So before we are taking the product modulator, so initially binary bits are the sine omega ct, and here we are taking the one carrier frequency. So that is the cos omega ct by 4. So from this one we are connecting to the product modulators. So that is the one is the high frequency of the signal omega c plus omega t by 4 and omega c minus omega bt by 4. Next one we are taking the modulation of the signals. So and next one we are summation of these signals. Finally we are getting the sub. This is the MSK of the modulator. So before this one, here we are taking the one more of the modulation technique. So that is the root 2 PS. Root 2 PS and the root 2 PS. So now S of t equal to root 2 PS sine omega ct into cos omega c plus omega bt by 4 plus root 2 PS cos omega ct into sine of omega c minus omega t by 4. So based on this equation, so we can find the Euclidean distance. So that is the in the phase angle of this one. So one is the root. So for example, let us assume this is the one amplitude modulation. This is the another one. So by this one we are getting the root 2 into ES. This is the Euclidean distance between this phase angle as well as this one. So that is the root 2 into ES. So where ES equal to 2 into EB. So root 2 Euclidean distance of this one root 2 ES equal to, so ES equal to root 2 into E. This is the MSK modulation system. And coming to the MSK detector, so here we are taking the S of t, so that is the input of this MSK detector. Next one again we are giving to the product modulators. Again we are giving the product modulators. So next one connecting to this low pass filters, and this one also one more low pass filter. Next one here we are connecting to the another filter. If it is required to the FIR filter, take that FIR filter. So after that we are taking the decision making device. So then we can select that bit is the 1 and 0 based on this low pass filter and this one. So this is the PM1 and this one is the PM. So this is the MSK detector and the receiver. So advantage of the MSK is the constant amplitude and the smooth phases. So why? Because constant amplitude. So this is the minimum shift keying. So it is depending on the phase angle only. It is not depending on the amplitude of the signal. So that's what the amplitude is the constant and the phase is the smooth. So power efficient also there. So it is not depending on the band pass filter. So why? Because the continuously phase angle is there, so bandwidth is not required for this one. So faster diagnosis and the lower cost. So coming to the disadvantage of the MSK, so that is the complexity and the phase jitter. So it is a synchronous of that particular phase angle. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.